This is Mr. Hansen's sophomore honors physical science class notes. These notes are meant to be viewed for Tuesday's class, January 20th, 2015. And we are talking about the transfer of thermal energy, which includes conduction, convection, and radiation. I've chosen to use a PowerPoint just to see how the students like it, see if you guys like this view a lot better, and if you can actually read it a lot clearer than writing on the board. So what we have already learned, we have the kinetic theory, which is a theory that pretty much states that all materials are made of particles, atoms, ions, molecules, that are in constant motion, or always moving. The thermal energy of an object is how much potential and kinetic energy the particles within that object have due to particle spacing and how much those particles are actually moving. Temperature is a measurement of thermal energy. Now remember, thermal energy and mechanical energy are two different things, because mechanical energy is talking about an object, and thermal energy is actually talking about the particles that make up that object. So when we actually stick a thermometer to a table, we're measuring how much those particles are actually moving. We have the temperature scales, which are Kelvin, Celsius, and Fahrenheit. In here, we will only deal with Kelvin and Celsius. We talked about converting between those. And then we have heat. Heat is thermal energy flow, and it always flows from objects with a higher temperature to objects with a lower temperature. And what one object gains is the exact amount the other loses. And then we had specific heat. Specific heat is the amount of energy needed to raise 1 kilogram of an object 1 degree Celsius, or Kelvin. Which brings us to conduction. Conduction is a transfer of thermal energy between colliding particles, or particles that are in direct contact. We underline the word direct because that is actually important with this one. It's important also to note that particles vibrate but do not move from place to place. So it kind of sits in its exact place and just kind of shakes or shifts from side to side. But the particle does not actually change position. It is usually observable in solids. That does not mean that it cannot happen in gases or liquids. And it utilizes thermal conductors. Thermal conductors, we'll talk about those a little bit later on. Some things are better for conducting heat than others. Here's a picture of conduction that I found off the internet. It has a metal rod and a fire. You could think of that as a coat hanger, maybe a marshmallow, making a s'more or something, and you hold onto that coat hanger too long, and that heat is transferred from the lower end slowly to the higher end. Now this might actually happen faster depending on what material that rod is made of. And there again we're getting into the thermal conductor or thermal insulator area. The second way that thermal energy is transferred is through convection. And that is a transfer of thermal energy in a fluid by movement of the fluid from one place to another. And I did underline the word fluid, and I'll go ahead and jump to the second bullet. Fluids flow, and that is anything that can move past itself, which includes liquids and gases. A lot of people just think that's liquids, but actually air, the atmosphere, is a fluid. Particles actually change position, so unlike conduction, where the particles kind of vibrate in place, these particles will move. They will change position. This causes convection currents. Convection currents is pretty much the rising of warm and the falling of cold. And that goes off of density. As things gain thermal energy, they start taking up more space. They move around a lot more. They bounce off the sides of whatever container they are held within, and they push out. And then you have less particles per unit area, or unit volume is a better way to say it. And if there's less particles or less mass per volume, it is less dense. So that warm that takes up more space actually rises because it is less dense than the cold, which has less energy, and the particles are closer together, and the cold falls. This actually has a big play on our weather. which is how we got to this slide. Another picture I got off the internet. It's just showing the warm air rising, and it has moisture in it. As that warm air rises and brings up the moisture high, the cold air falls. And eventually what happens is that air can no longer hold the moisture that it's carrying, and it rains. And this is a lot of times in the summer when you see a real dark, intimidating storm coming in, and you feel that gust front, that cold gust of air. You're actually feeling that air drop its moisture. And getting back to specific heat, that water holds much more heat energy than the actual gas does. So when it drops that water, that warm rain, it doesn't have that much heat anymore, and it drops and falls back down. And this is a cycle that just happens over and over. This is why the warmest bed in the house is the bunk bed and upstairs during the summertime, and why you want to hang out in the basement during the summertime as well, because it's cool down in the basement. The third transfer of thermal energy is radiation. And this is the transfer of thermal energy by electromagnetic waves. They may pass through solids, liquids, and gases. And the way I always like to put this is, it includes things that glow. Think of the sun, think of sitting next to a campfire. It says, remember electromagnetic waves. They can go through space. We had mechanical waves, which actually required a medium to transfer. Well, electromagnetic waves don't require a medium. They can go through void. They can go through space, which is extremely important because the sun powers everything we do on Earth. Radiant energy may be reflected, passed through, or absorbed by matter. It depends on the material. Darker materials absorb more. This is why in the summertime you don't want to be wearing a black shirt. The glow from the sun, more of that thermal energy is absorbed by that black shirt than if you were wearing, say, a white shirt that reflects a lot of it or lets some of it pass through. It's also why most people don't have black houses. There's a lot of ways we could have went with the picture off the internet for radiant energy flow. But I like this one because I want to put an emphasis. There is no fan here. This is just a space heater that's just sitting there and glowing, kind of like the inside of a toaster. And as it glows, the guy reading the book there feels that thermal energy on his skin. It's also a good point if in the spring when it's cool outside, but it's still sunny, in the shadow of a tree, it's cool, and you walk out from underneath that tree, and you feel warmer. The air temperature is no different, but your skin feels warmer because you're actually absorbing more of that radiant thermal energy. So what we have here are examples, and by tomorrow what I'd like to see is I'd like to see 5 examples, and you guys can use the internet, you can use resources, family members, your book. This is chapter 14, section 2. But I'd like to see 5 examples of conduction, 5 of convection, and 5 of radiation. It should say radiation. I don't know why I left an S on there. I looked for a picture that would represent all of them, and this one was relevant. We have the conduction and the handle, and this is why the handle is not usually made of the same material that the pot or the pan is, except for with maybe cast iron. In cast iron, you don't grab with a bare hand because it hurts. Then we have the convection currents. As the water boils, the warm rises, cools, and falls down. You can also think of that actually as the steam above it as well. Steam rises. It doesn't go to the side, it rises until it cools. Now, if this pot was directly on there, that would be conduction. But right now, if you put your hand just right above that stove or a little bit off to the side of the burner, you can feel the heat even to the side because it is glowing. Okay, that's the end of the notes. We'll see you tomorrow.